Okay, state the domain of the rational function. Well, remember, denominators cannot equal 0. So any of these questions, if I set the denominator not equal to 0, that will give me the domain, okay? Okay, so hopefully you can see that if I put a 12 here, I'll get a 0. So x cannot be 12, all right? In interval notation, that's negative infinity to 12, and then 12 to infinity, okay? Now this literally is x cannot be 0, okay? So again, negative infinity to 0, and then 0 to infinity. Now this one needs to be factored. The denominator is x plus 1, x minus 1, if I factor that difference of squares, x squared minus 1, okay? Both of these parentheses cannot equal 0, so can you see x cannot equal negative 1 and x cannot equal positive 1 in interval notation. That's negative infinity to negative 1, negative 1 to positive 1, and then finally 1 to infinity, okay? No different this one at the end, question 4. That'll just factor into x minus 7 and x plus 2. So therefore x cannot equal 7 and x cannot equal negative 2. So again, you would write it something like that one there, interval notation. Okay, so those are domains. Now, this is relevant because it applies to this next part here. New topic maybe about vertical asymptotes. The vertical asymptote is a line on the graph that the graph cannot touch. Okay, the function cannot touch because it involves the domain of the rational function. Okay, so if you found the domain of the rational function, this is also going to be the vertical asymptote, all right? So let's clear all this up here. I'm going to do the same thing again with these next questions. Right, again, can you see this? X cannot be negative 8, okay? That means the vertical asymptote is negative 8. X equals negative 8. In other words, if I had a graph, this is what I would draw. X equals negative 8. And the graph of the function cannot approach that line. Maybe it looks something like this. Okay, or like this. But you see, this graph, this part of it, cannot touch this vertical line. Okay, so that's the vertical asymptote. Very similar to doing the actual stating the domain of the rational. So here we go. Here's one. Can you see the vertical asymptote? X equals 2, because that's what you can't have, because it would make the denominator 0. This is a trick question, okay, because this will never be 0. If you square something and add a 5, if you square anything, it's a positive answer. If you add a 5, you'll just make it bigger. That's a trick question, okay? At least for the vertical asymptote. Of course, for the horizontal, I've got to do something different. We'll come back to that. Again, with this, I'm going to factor this. X squared minus 4 is x plus 2, x minus 2. So can you see, if for the domain question, x cannot equal negative 2, because I'll have a 0 there, and x cannot equal positive 2, because I'll have a 0 there. In other words, x equals 2 and x equals negative 2, sorry, wrong way around there, it doesn't matter. Those are the vertical asymptotes, okay? So, there we go, okay? Right, now, finally, this looks very similar, but it's a little bit of a trick question. The reason is this. If I was to factor this denominator, I'd get x plus 5 and x minus 5. But can you see here? Look, this will cancel that. Can you see that? All right? Now, this will come into something later where there may be a hole in the graph, but we'll deal with that later. Okay, so this is actually just 1 over x plus 5 if I reduce it. Therefore, x equals negative 5 would be the vertical asymptote because I cannot have negative 5. Okay? So that's how you do the verticals. Now, the horizontal is just a whole new thing. The vertical asymptotes is just a continuation of this domain of rational functions up here. Now, the horizontal asymptote, well, really, there's just the 3 rules, and it's this. Okay, I'll just give you a quick run through. If I have a bigger order of the x on the denominator, it's always y equals 0. The horizontal asymptote is basically the x-axis. That's y equals 0. If I do something like this, again, if that leading term is larger on the denominator, if the order is bigger. If I did this, okay, all of these would be y equals 0. Okay, so that's it. That's just one rule. Just one rule there. Now, how about if they're the same order? So if I do something like this, x over x, or x squared over x squared, or x cubed over x cubed. Well, how it works is you look at the leading coefficient. So although I've made all these 1, if I was to write this, 2x over 1x, so y, the horizontal asymptote, is going to be 2 over 1, which is just 2. Okay? If I write 3x squared over 1x squared, the horizontal asymptote will be 3 over 1, which is 3. If I do something a bit more obscure, like 5x cubed over 2x cubed, the horizontal asymptote would be 5 over 2. And that's it. It's just a rule to remember. Okay? Now, if it's larger order on the numerator, we end up with a slant asymptote or an oblique asymptote, but we're not actually covering these in this class. Okay? So we're just looking at, say, something like this one. Here we go. Right. This is y equals 0 because there's a larger order on the bottom, on the denominator. Okay? Now, this is an x over an x, so the order is the same. So this is y equals 2, because think of it as 2 over 1, okay? Again, with this one, this is y equals 0, because there's a larger order on the denominator. Again, with this one, this has got both x squareds, so I look at the leading coefficient, which is 5 over 1, so this would be y equals 5. And finally, again, with this larger order on the denominator, so y equals 0. Hopefully that's okay. The only ones I had to look at was this one and this one, where they both had the same order of the leading term. So I just looked at the leading coefficients both on the numerator and the denominator. And that's how you do the horizontals.